In this lecture, we look at the translational kinetic energy and also the mean free path of a gas atom. The average translational kinetic energy of an ideal gas atom is given by K, with a bar on top, which is equal to 1/2 times the mass of the atom times the root mean square velocity squared of the atom. This average K is equal to 1/2 m times the root mean square velocity, but we've plugged in the temperature dependence of the root mean square velocity. What that is, the square root of 3 times r times the temperature divided by the molar mass. And then we square that, it gets rid of the square root. And we have 3/2 times the mass divided by the molar mass times RT. Well, the mass divided by the molar mass is equal to 1 over Avogadro's number. So we can write this as 3/2 times RT divided by Avogadro's number. And then if we define R over N to be a new constant, we have that the average K is equal to 3/2 kT. So the average translational energy is equal to something which depends only on the temperature. So this K is known as, this little k is known as Boltzmann's constant, and K is equal to R divided by N by the Avogadro's number, which is equal to 1.38 times 10 to the minus 23 joules. This is another case where we see an explicit connection between a microscopic value, this translational kinetic energy, and the temperature. What is the average distance a molecule travels before colliding with another gas molecule? Well, here we're showing a gas molecule bouncing around when it runs into other gas molecules. And you see sometimes the path between collisions is long and sometimes it's short. The average of those paths between collisions is and it's symbolized by lambda. It's equal to 1 over the square root of 2 times pi times the diameter squared times the number of atoms in the volume divided by the volume. D is the diameter of the molecule, so if you increase the diameter of the molecule, then 1 over d squared gets smaller, which reduces the mean free path as you should expect, because if you make the molecules very large, it's very likely that they'll collide. Similarly, n is the number of molecules, so that 1 over n gets smaller as you increase the number of molecules, and again, the mean free path goes down as you add more molecules into the box. Let's look at an example with respect to the average translational kinetic energy of an ideal gas atom at room temperature, or 20 degrees C, and then again we'll look at that atom on the surface of the sun. Well, we have to convert 20 degrees C to Kelvin, so the room temperature is equal to 293 K. The average translational kinetic energy is equal to 3/2 K times T room. Plugging in the numbers, we find that this kinetic energy is equal to 6.1 times 10 to the minus 21 joules. If we do the same for the sun, well, the only thing changing is the temperature. So now we have to put in T sun in our formula. And the temperature on the surface of the sun is around 6,000 Kelvin. So the value comes out to be 1.2 times 10 to the minus 19th joules. Let's look at an example where we look at the mean free path of 1 mole of O2 confined to a liter, or to a cubic meter. You might recall that a liter is 10 to the minus 3 cubic meters. So if we look at the mean free path of O2 in a liter, we have our formula, and we also look up that the diameter of O2 is equal to 2.9 times 10 to the minus 10th meters. Then we plug in all our values. We have the square root of 2 times pi times 2.9 times 10 to the minus 10 meters squared times 6.02 times 10 to the 23rd, the number of particles in a mole, divided by the volume. And we take 1 over that to get the mean free path. And that's equal to 4.4 times 10 to the minus 9th meters. If we do the same thing for a cubic meter, we find out that the only thing that changes is the volume, so that we end up getting the value of 4.4 times 10 to the minus 6 meters. So there's quite a bit of space if you put 1 mole of O2 into a cubic meter box, so the molecules can travel 1,000 times farther than they can if they're shoved into a liter.